In this video, we're going to look at three different methods of displaying live location tracking on a web-based map. We will be using not only GNS, but LoRaWAN, Wi-Fi, the Things Network, Colos, Google, and Node Red. We will also try to employ technology that's under your control and minimise the use of cloud-based services. It's not perfect, but is at least the first few steps on the journey of assembling the capability of mastering real-time geolocation. These are three designs of me that may be constructed, but are based on Kevin Nichols' original presentation at the Cardiff IoT meeting in November 2018.
Kevin's way.
So, hello, I'm Kevin, and I'd like to start off just by saying, Richard, utter.
It also links into Stuart's site, LoRa Tracker UK. Stuart has been involved in the many uses of radio communication for many years, including the tracking of balloons. He's also the only person I know who has designed and had the Russians launch his own homemade satellite.
I bloody love this.
Tracking that as it moves at over 17,500 miles an hour is no small task. But back to planet Earth. We appreciate that our endeavours here are built upon a great deal of community work and hope that we've referenced them correctly. In actuality, this event comes about because of the availability of kit rattling around at the bottom of our component drawers at the time. An advantage of this is that all of the designs are inherently low cost. Let's begin this video on geolocation using GNS, Wi-Fi and LoRaWAN. In the first example, we're going to use a traditional GNS, Global Navigation System, device to fix location. You will understand from experience using GNS on a mobile phone that GNS has its limitations. It relies on the constellation, or more strictly speaking a series of competing constellations of satellites that circle the Earth. Their signals are faint, meaning that they are probably not available indoors or where a clear view of at least 4 satellites is possible. They are, however, accurate to less than a metre right across the globe. The cost is that GNS devices consume relatively high power levels. This is a particular problem when dealing with battery-powered devices. This diagram displays the path and components. The location is fed from a small conventional GPS receiver into a small processor which sends it back via LoRaWAN radio to a local gateway and then onto a Network Things server via the internet. There it is processed and forwarded to an application running on a Pi. The Pi formats the data and displays it graphically using Node Red. GNS is not used in the second example. Here we rely on a myriad of local home and business Wi-Fi routers that split out their signal into the neighbourhood to be detected by passers-by. As Google trawl the streets updating their Street View images, they also monitor Wi-Fi. They record the varying signal strengths and map them back to each router using their public identities called SIDs. These SIDs are the names seen listed when you scan Wi-Fi using a mobile phone. It's a good system until you move a router to a new location. Radio signals grow weaker as you move away from the transmitter. By comparing the power of 2 overlapping SIDs, it's possible to take a rough guess as to your location. Note though that using this technique you could appear here or here, where the same relative readings could be taken. The accuracy of the location could further be compromised as radio signals may be reduced by walls or reflected by buildings. Here is an unnecessary waste of power, causing a radio shadow and loss of signal. Wi-Fi signals do not tend to travel too far, and in built-up areas can be found coming from many sources. Geolocation using this technique is therefore a fair guess, although I'm not sure how the system deals with the excellent service emanating from our passing buses. You do not have to connect or associate with Wi-Fi access points to gather these power readings. Knowing their passwords is therefore unnecessary. The advantage of the system is that it is relatively cheap, reasonably accurate, but requires access to Google to operate. Technically, it's also possible to use the hundreds of mobile phone transmitters to calculate location. Viewers to the Channel 4 programme Hunted will know how the hunters triangulate in using these giveaway signals. Here we see it's the signal levels of the local Wi-Fi that are received by this small WeMOS board. It uses an on-board antenna. There is a pin-for-pin mapping between it and the LoRa board, which allows very small units to be made. The WeMOS board has a small ESP8266 processor that forwards the details via LoRa onto the gateway and then, as before, to the Things Network. Node Red, running on the Pi, extracts the readings, as before, from the Things Network. This is then combined with the data requested from the Google database of Wi-Fi signals and shown on a Google map. LoRa example. The third option involves Colos. Colos is a project that's been set up to use the local LoRa radio signal levels for triangulation in the same way as Hunted used mobile phones above. It is, however, an entirely different approach to acquiring location. Whereas examples 1 and 2 use GNS and Wi-Fi to passively geolocate using received download signals, this option is active. The node actively transmits an upload signal back in the opposite direction in an attempt to expose its location. Paradoxically, even though this technique requires the power to transmit, this option uses the least power of the 3 examples. The disadvantage is that it requires good LoRaWAN coverage to work correctly. It works like this. All gateways in the area promiscuously forward any packet they receive to the Things network for analysis. As part of their function, they check and wrap every package with additional metadata about each packet. This metadata includes the date and time received and an indication of signal strength. This metadata is important to the system, as it needs to be able to identify all of the duplicate packets received. Only one aggregated copy of any packet should survive and be passed to the final application. It's also the details held in the metadata that allows the system to calculate the single best return route to send packets back to each and every node. Colos, on the other hand, must have duplicated metadata in order to function. It requires a packet from at least 3 gateways to triangulate. It performs its calculations both on either the strength, the timing, or both the strength and the timing of the received signal at each location. We have already discussed the problem involved in using radio signal strength, and timing is no easier. To faithfully record the exact TOA, the time of arrival, of each packet, highly accurate clocks at each gateway are required. Errors in timing or sloppy reporting of a gateway's location will result in positional inaccuracies. With all of these factors taken into account, Colos estimates location and provides a plot. We can plot the relative advantages and disadvantages of each of these 3 examples. Before describing any further the hardware and software used in each example, we will now consider the key step in controlling your LoRaWAN radio environment, setting up an account with the Things network. To be able to achieve everything in the Things network, TTN, you have to apply for an account. It's not just open source and very friendly, it's also free and very easy. Head for https://thethingsnetwork.org. Click Sign Up. Enter the username you'd like to be known as. Be creative, as many thousands of users have passed this way before you. This name is immutable and may not include spaces. Enter your email address and the password you'd like to use and press Create Account. If all is acceptable, respond to the confirmation email that the site sends you and return back to the Things network to log in. Congratulations! The Things network is an impressive and growing site. There are many options to investigate, but here we are concerned with its functionality. The Things network account provides 2 central services that are apparent once you've logged in and selected Console. These are Gateway and Applications. The Gateway option is the gateway to all of the facilities that allow you to set up, maintain and monitor the gateways you may wish to deploy. This is covered in another video, but this video does assume that you already have some connection to a local gateway. In fact, it's a must. Here we are interested in and will concentrate on applications. Applications are, as the name suggests, all of the different projects you run under the Things network. Applications is also the heading under which all of the nodes running a particular function are grouped. A group of air quality nodes will operate under one application, slurry level measurements under another. Here we're going to run 3 separate applications, one for each of the examples we've previously described. Shown here are a list of some of my existing test applications. Applications are where all of the details of the individual settings are maintained and controlled. At first sight, applications can appear a little daunting, as they involve many similar names, but these will soon become familiar with use. One thing that the use of these many terms promotes is good record keeping. Being clear about every title and value will save a lot of time, errors and frustration, believe me. Let's now see what these terms mean and how they map across into the examples. Please note that all of the details mentioned in this video are referenced in the space below. Programs, sketches and other notes are provided and updated in the GitHub. This is the hardware for example 1, the GPS tracker. It consists of a GPS receiver, an Arduino Pro Mini, an RFM95 radio module mounted on a Pro Mini motherboard. a connector and aerial, although to reduce the cost, just 86mm of wire can be installed directly to the board as an antenna. Note that the antenna should be connected before the unit is powered up, as damage can occur otherwise. This is the case with all similar RF devices, despite the low power level used. The wiring should be obvious from the video, as everything is visible and clearly marked. An FTDI board set to 3.3 volts, not 5 volts, is plugged in to power and program the board during development. All of the power and signalling is sent via the single USB port of a host machine, and this completes the hardware description. Software, the Arduino IDE. The Arduino is programmed using the Arduino Integrated Development Environment, the IDE. This is a really popular programming environment and may be downloaded from http://arduino.cc. Use of this IDE is very well documented elsewhere, but this is what it looks like once it's been installed. A newly downloaded version will look significantly cleaner than mine displayed here. All of the additional options, pull-downs and clutter that appear on this copy are the results of years of use. The reason that this IDE is so popular is because of its flexibility. It will operate with a growing range of different boards and designs. Here, we needed to configure and operate with our chosen board and processor. Once again, we've already covered this IDE in much greater depth in earlier videos, so we'll motor on with just the key changes here. The important configuration details are: select Tools, Board, and Pro or Pro Mini. Reselect Tools, Processor, and this time select AT328P 3.3 volt board. If these options are not available, select Tools, Board, and Board Manager to reveal the Board Manager. Enter Pro Mini into this search box, which should reveal the Arduino AVR boards option. Select Install. You may need to restart the Arduino IDE for this change to be recorded. Then select Tools, Port, and select the correct port for the board you've connected. Port options will vary here due to the local host and particular connections you have. And should you have trouble selecting the correct options from a slew that may be offered, the advice is to disconnect any unused devices, and hopefully the only remaining port is connected to the Pro Mini. Otherwise, this is a slow job working through every option until something bursts into life. Clicking on Check Board Details is a very good way of confirming the correct connection. This should complete the IDE setup, although I'm sure I'll recall some missing option after this video has been uploaded. Do check the comments below. With everything set up, we now need to grab a copy of the program from the GitHub and modify it for our use. Paste the program into the IDE. In Arduino terms, this short program is called a sketch. We do not have time to do a line-by-line explanation of the sketch, just comment and explain the important individual changes that will be required to get your copy to operate correctly. As an aid, we've left further comments in each sketch to provide further assistance. To simplify things further, all of the references here are made with the European configuration. Apologies to the rest of the world. Opening two windows side by side may be the easiest method of mapping TTN details into the Pro Mini's program. In the TTN console, we first need to add a new application and then add a device to the application. In the process of defining and identifying our application and device, we will be granted names and keys that configure and open the system for our safe and unique use. This is how it's achieved. From Applications, select Applications. At the top of the screen, select Add Application. 4 fields appear. Note their names carefully. Application ID, Description, Applications EUI, the Extended Unique Identifier, and Handler Registration. Applications ID. This is the name that's going to be carried across all references, so make it meaningful. It's a unique identifier. It does not explicitly say so at this stage, but there are some restrictions to the name. First, it has to be unique. All characters should be alphanumeric, lowercase, and non-consecutive, no spaces, and it may not start with a minus sign or underscore. Apart from that, the choice is yours. The border on the form remains blue if the system is happy on completion, but turns orange otherwise. Description. This is the application's description. There are other descriptions later, but this can be any human-readable content that describes the overall function of the application. Application EUI. Unless you have a very good reason to enter this, which you don't, let TTN allocate the application EUI. Finally, leave the handler as suggested. It's selected to suit your region. Pressing Add Application should cause several green flyouts to appear, along with this screen full of further navigation. This overview confirms the details from the previous page, and there's a good live feel to this well-designed interface. This timer displays the time of creation of the app. This is a style being duplicated elsewhere. Applications EUI. Applications EUI have been allocated by TTN, and here is the source of lots of potential problems. By default, the app EUI is displayed as a 16-digit hexadecimal number. It may be copied just by clicking on this small icon, but on this occasion, our code requires a different format. The same number can be redisplayed by clicking these greater than and less than characters. This is an alternative method of describing the same number. But to confuse things further, the layout of this format may have the most significant byte or the least significant byte set first. It can be switched using this dual arrow swap icon. Least significant byte first is referred to little endian and is the format required in our first example. Click this button to copy it to the clipboard. With the application now fully established, we now need to progress to the next step, to add or register a device or devices with the application. This is achieved here. Clicking reveals more fields with similar and potentially confusing names. The device ID is another immutable setting that cannot be longer than 36 characters and has the same constraints as the application ID name. A green spot here confirms an acceptable entry. The device EUI is where the device EUI may be entered. This is supplied by the manufacturer of the radio device. It's equivalent to the MAC address on other network devices, but may be overwritten at this stage. It's not immutable and may be changed later. Enter your device EUI if it's been provided, otherwise overwrite your own 16-character hexadecimal option. The device app key is a 32-byte character. Let the system deal with it. And finally, the app EUI is duplicated from the page before. Correctly entered details are confirmed by the register button turning green. This is a nice design. Press the green button to reveal this summary page containing all of the details. Two final comments at this point. The first is trivial. This small yellow dot is a valuable indication of good operation. It's very satisfying when this turns green later, when the setup is successfully completed and the connection with TTN established. That represents a major achievement. The second is important but does not matter here, as the default offered is acceptable. I'll mention it here as this is a key concept and convenient to introduce at this point as an aside. By now, everybody should be used to connecting to a Wi-Fi system, a process called association. In LoRa, this joining process has the far less dubious and proactive term activation, and there are two methods of activation. These are abbreviated to ABP and OTA, activation by personalization and over-the-air activation. The reasoning behind these two methods might be explained by suggesting that ABP is the quick and dirty method where joining and hence security details are stored in the node, where OTAA is a slightly more complex interchange that's much more secure. It's also the method that's more convenient when scaling node manufacture into high numbers. We see here that the default is OTAA. To toggle this, click on Settings. This page reveals the activation methods. When the ABP button is pressed, the page changes to reveal yet more fields. Device address, network session key, and application session key. You can perhaps now see why good housekeeping was mentioned earlier. Don't become downhearted when I say this is not the end of it. There is yet more to come regarding security. When using ABP, it's these values that need to be inserted into the program on your node in order to successfully join. Different values are recorded in the sketch depending on whether ABP or OTAA is required. We will use OTAA as the default selection at the moment. The important point to note is that the values have to be copied over from the device section into the sketch, as these are the marriage vows that couple a device with TTN. Let's revert to OTTA and complete this aside. With the program updated, click File, Save. A compilation check on the sketch may be initiated by pressing this tick button, and if all is well, transfer the program to the Mini Pro by pressing this right arrow button. Progress of the upload is shown by this bar, and final confirmation of success displayed in this text area. The program runs immediately the upload has completed. The function of the upload connection then changes to receive responses from the Pro Mini. This is the usual behavior for any device using the Arduino IDE. The return details can be seen by holding the Control and Shift buttons together and pressing M. This opens a useful monitor screen. Returning to this TTN page, and the amber button should have turned green. Communications has now been made, but what has been sent? Click on this data button and the packet should be seen arriving periodically. Each line is a new packet. Here's the time, a counter and a port. An important term here is payload, the hexadecimal data. Clicking the blue twirl down arrow reveals the encrypted data again, and the metadata encapsulating each packet, as mentioned earlier. Notice this important term uplink. Uplink is the connection from the node to the gateway. Returning data from the gateway to the node is called the downlink. Here we can see time, date, frequency, data rate, and other details about the packet, but underneath a further copy of yet more metadata regarding the packet as it was received by each of the gateways in the region that received it. All of these duplicate packets have been forwarded by the system as a single entity. We will return to metadata later. For the moment, consider fields. Here we see fields decoded. All of the data in the payload nicely displayed in plain English. This is good, because from the point that it left the node to its appearance here, everything has been encrypted. Part of the security of the overall system is that all packets are encrypted. The encryption details are those that were arranged during the join process, the ABP or OTTA mentioned before. So, can we see each end of the encrypted pipe? The answer is yes, but there is a slight added level of complexity. We have to look at a further optional stage called compression. The complete system only works efficiently if all nodes pass minimal radio traffic in the shortest possible time. In fact, on the radio interface, there are not only limitations on the data rate that bits can be transmitted and the size of the packets they can be contained in, but there's also an overall restriction on the total time each node can spend transmitting. This can be as severe as only 0.1% of total time. To achieve the maximum throughput performance, bits and bytes have to be manipulated to make the very most of the transmission opportunities. In our example code, this is done here in the sketch. There's no standard code for this section, as every application will be designed to carry different data. This section will be unique in every case. Data compression and bit manipulation are more fully covered in yet another video. TTN deals with the compression and decompression of packets under the heading Payload Formats. Clicking on this option displays 4 custom options: decode, converter, validator, and encoder. These options offer the opportunity to enter 4 short JavaScript programs, one for each stage, to compress, decompress, and validate data. These little snippets of code are inserted into the chain of packet handling, modifying, validating, and making sense of the raw unencrypted data. We'll see this in operation in the next section. To review and possibly clarify this first section. In this first section, we use the conventional GPS system to recover location information from the constellation of satellites orbiting Earth. Typically, we need to see 4 clearly for the receiver to lock on and provide a stream of location and timing data sentences. The processor picks out the vital data and compresses them into data packets. The radio device modulates the data for radio transmission. All gateways receiving radio packets surround them with metadata for onward transmission to the Things network, where they are sorted, decrypted, and made available to qualified viewers. One view is via the console screen. So let's take a look at that now. This is the application's data screen. A new block appears for every reconstructed packet that arrives from any of the devices that are registered with an application. This example only has one at present. The time, the counter, and the port are displayed along with the sending device ID and the payload in hexadecimal. The sense that the payload functions have made of the packet are revealed here. Click on the blue twirl down expands each packet. Here, the uplink payload again, and the decoded fields, and beneath it, metadata. The time, frequency, and data rates are provided, but then there's a section labelled Gateways. This is an assembly of all of the gateways that received a copy of the same packet. Each gateway has stamped its identification, timestamp, time channel, and location into the packet. The 2 values labelled RSSI and SNR are the 2 measures of recorded signal strength. The more gateways that receive the packet, the more sections there will be under gateway. This completes the overview of the TTN console and how it handles packets. With data being correctly received at TTN, we can now move on to the next step, Node Red. If all has gone well, the sketch has been uploaded onto the Mini Pro. The GPS is receiving correctly, and the details being transmitted via LoRaWAN to TTN. These details now need to be recovered to be processed. In this first example, we are going to use the Raspberry Pi and Node Red to do the heavy lifting of collecting data from TTN and positioning the batten onto the world map. Node Red, when supplied on the Pi, tends to run a little behind the very latest version available on the web. Step 1 is therefore to upgrade or install this to update it to the current version, and step 2 is to go further. Here, we need to add 2 additional Node Red modules that are not supplied with the standard distribution. These contributions, as they're called, include mapping functions, dashboards, and methods of contacting TTN. Step 3 is then to run the flow. I should begin step 1 by suggesting that this upgrade could go wrong, and that any precious data be backed up before undertaking this process. That said, point the browser on the Pi to nodered.org/docs/hardware/Raspberry Pi. That page displays a link to this command, which may be copied and pasted into a terminal window. This excellent script begins with a few questions before installation. This will take a little time, but on completion allows Node Red to be started at the text prompt by entering node-red-start. Little appears to happen as Node Red operates in the background only, revealing its useful operation via a browser interface. Inspecting the printout provides a reference to this browser link, which is either your IP address :8080 or, more generally, http://127.0.0.1:880. If this opens, all is well with the Node Red installation. You can, of course, move to any machine on your local network and insert the name or IP address into the browser to see Node Red running remotely. But do not forget the :1880/ at the end of the address to select the correct port. We can now move to step 2, installing the additional modules. There are direct commands that can be entered in at the prompt to install modules, but perhaps the simplest method is to click on this hamburger icon here to reveal the Palette Manager option. Here are the 2 tabs, Node and Install. There are 2 additional modules that need to be installed, TTN and World Map. The first is to install TTN nodes. Click on the Install tab and enter TTN into the search bar. You may as well enter all of the options available. There are these 2 currently. Press this Install button in each option. Up to now, we've been using the term node to mean the thing or end device. In Node Red terminology, nodes are these on-screen elements held in the palette on the left. Next, we will install mapping functions. Enter mapping into the search to see the available updates and select this one. Press install and wait for a few moments. I've speeded up this video. It's probably wise to restart Node Red after these upgrades. Mouse click in the text window and enter Ctrl+C to reveal the prompt. Enter node-red-stop and then node-red-start. Watch the resulting lines to check for errors. After the restart, the nodes should appear in the palette. If they have, we can progress to the third step, importing the example1 flow from GitHub. One of the many joys of Node Red is the very simple method of designing or importing designs. Interconnecting nodes are called flows and are formed by dragging nodes onto the canvas and connecting them by left mouse clicking the small grey input and output circles at either end. There's no limit to the number of inputs or outputs that may be coupled in this way. Blue circles and red triangles warn of incomplete setups. Double-clicking on a node reveals a flyout with elements that require configuring. Once complete, click on this red deploy button that should clear all of the warnings and start the flow. Importing designs is simple. Designs are stored as text files. Head for the example1 Node Red flow on the GitHub. Simply copy the example1 sketch into your clipboard and click the hamburger icon Import Clipboard to open this window. Click the new flow and left-click in the grey pane and right-click to paste in the flow. If all is well, the import button turns red to press it. The graphic of the flow appears, attached to the cursor. Drop it into place using the left mouse click. This is a relatively simple flow, but has to be configured to suit your situation. The first blue TTN node has now been replaced by the uplink node, but performs the same function. It's a node that collects data from TTN. Double-click it to reveal this flyout. It should have 4 parameters: name, app, device ID, and field. I've inserted name, which you're welcome to change. App is the next field. This requires some important settings, so click this pen icon to access this flyout. This is where the node is linked to your application. Enter exactly the ID as it appeared earlier in the TTN site. Then enter the region or the broker. Again, this is available from the TTN application page. Finally, wind to the base of the application page and cut and paste the access key from the TTN page into the Node Red field. This allows Node Red to complete the first stage of the security settings mentioned earlier. Click Update to complete this stage. The earlier flyout reappears. Now, the device ID, again copied from the TTN page, needs to be pasted across. Completing this phase, suppress Done. Nodes that have been edited support this little blue dot on the top right-hand side. We've tried to keep this example as simple as possible to get you up and running in the shortest possible time, and in the process demonstrate how brilliant Node Red is. The second node is the workhorse, a function block. Double-clicking this reveals the JavaScript code within. Here we see how Node Red works. Short snippets of JavaScript designed to quickly pass on messages in payloads, a little like a hot potato. This node formats the payload ready to be passed to the third and final world map node. Clicking on this reveals the options that you will adjust to configure the system to operate with your parameters. To complete the flow, click on this Deploy button. It records the changes, clearing all of the outstanding blue dots, and begins the flow. A little housekeeping involves selecting this Debug tab to receive feedback about the performance of the flow, and this dustbin to remove any legacy notifications. After a small pause, a drop-down notification confirms that all is operational. As further confirmation, this green connected dot appears, showing that the parameters have been correctly configured and Node Red is in communications with TTN. This is another significant and pleasing stage, but where's the output? By default, the selected map will appear at your address /world map. It may also be invoked by pressing the Ctrl and Shift key together and tapping M, the same combination used in the Arduino IDE earlier. The map should appear, and if all has been configured correctly, the button located correctly. All in all, this is a very impressive achievement for very little work. The options up here in the right-hand corner provide an impressive array of display options. This completes example 1. Making the map publicly viewable could be the next stage, and this involves exposing your Pi to the internet. A few essential precautions have to be implemented beforehand. All of this is beyond the scope of this video, but have been covered in earlier editions. Once the precautions have been taken, discover your IP address and use the port forwarding rules on your router to expose port 1880 on your system to global view. On that happy note, we will move on to example 2, geolocation using Wi-Fi. Wi-Fi geolocation. This is the hardware used for geolocation using Wi-Fi, just 2 small PCBs. The first is a WeMos board that combines an ESP8266 microcontroller and a Wi-Fi chip. The second is from our good friend Charles at CH21. His LoRa and Node board has an RFM95 radio module, a few support components, and headers to solder it. Again, an RF connector and a small antenna have been added, although a short length of wire would do. If nothing else, this looks good. It's based on Frank Speck's design, Build a Wi-Fi Localization Node, from the TTN Learn section linked below. The WeMos board is programmed using the same Arduino IDE that was used in example 1. Modifying the IDE to work with the WeMos board involves adding the board details to the IDE and then selecting the newly installed choice. To do this, select File, Preference, and copy this address into this Arduino Boards Manager URL, and save by pressing OK. Now head for Boards, Manager, and select ESP8266. Repeat the loop by returning to Tools, Board, and selecting the 8266 option. The IDE is now set up to use the board. Now we will need to tell the IDE where on your machine the board is connected. As before, go to Tools, Ports, and select your local port. And we're away. The example 2 sketch can be copied from the GitHub and pasted into the IDE window as before. Again, as before, return to TTN and add a new application and add the device. Once completed, copy back the details from TTN into the sketch. The path should now become familiar. Press Save and then the Upload button. Check that there are no errors in the text screen at the bottom. And we're away. The node should now be transmitting. You can confirm that the device has been recognized at the other end by the Things network by checking that this dot has changed from amber to green. The data streaming in may be seen by pressing this data button. The first half is working. Now to recover the data from TTN and present it on a map. Return to the Node Red. Copy the example 2 Node Red code from the GitHub and paste it into the new canvas using the imported clipboard function. Double-click on the blue TTN message or event node and the flyout appears. We need to set up this second application, so click on the pen button. The second flyout appears, and here transfer the application ID, the region or broker, and the access key. Click Update to return to the first flyout. Enter the device ID, and this time include this field as shown. We did not do this in the first example. Otherwise, everything else follows the same path. Press Done to complete this entry. We now need to set up the link with the Google side that's going to provide the Wi-Fi database access and mapping features. Google features are enabled and controlled using an application program interface, an API. Setting up and using the account to obtain an API tends to change, but this is well covered in their help files. The essential steps for gaining the security rights involve searching for Google geocoding and acquiring an API key. This is your private entrance to the system for your secure access, so don't go broadcasting it on any YouTube video. You may see the familiar pattern with the use of the API with Google and the access keys used with TTN. We can now work through the flow. These two function nodes prepared the contents to be forwarded to the Google application using this HTTP request node. The JSON node converts the reply before the message is passed back out to the Google mapping function to be displayed as before. Press Deploy, and here are the results. This final example just uses the LoRa signal to geolocate. It's technically the simplest to establish and is also the method that uses the lowest power of the three shown here. In addition, it has the advantage that it does not require any special software or hardware node. It simply involves registering the details of the node with the Colos project. The disadvantage of this method, however, is that it will only respond effectively in an area well covered by LoRa gateways. The reason for this is that the location is derived from either the signal strength or the relative TOA, time of arrival, of the signal at each gateway. 3 gateways zero in on the exact location, inside and even outside the triangle. Additional gateways are an advantage, but it's reported that improvements tend to fall off after 6 are employed. The packets transmitted from a node for geolocation purposes may be tiny, the shortest blip of information. Close to the gateway, this blip may only take a few milliseconds to transmit, but to operate at a greater distance, a larger spreading factor is required, causing the transmission to take longer, and in the process drain the battery more rapidly. There is also a further issue. Nodes just wake up and rudely just blurt out their packets of data with no regard to any other user on the system. It's a cheap and cheerful scheme that was used quite successfully in the original LoRa network, a predecessor of today's internet. Behaviour such as this may be acceptable when there are only a few participants, but as the numbers grow, the chances of 2 nodes transmitting at the same time and both signals getting scrambled and lost increases. It's called a collision. Only the Japanese system imposes courtesy on their nodes, where each device must wait for a moment of silence before transmitting. Everywhere else, it's a free-for-all. The accuracy of the system will therefore deteriorate as the traffic levels in an area increases. It will be interesting to see how this LoRaWAN function survives in the cities of the future. The hardware used in this demonstration remains greatly unchanged. The RFM95 LoRa radio module, the Mini Pro, and the LoRa Mini board from CH21, although here we also have our local champion Stuart designing and distributing his own boards that can be seen on loratracker.uk. The code here, downloaded from GitHub, should be familiar by now and is only the very minimal skeleton sketch. The values are cut and pasted across from the Things Network site. The final part in this jigsaw is the connection of Colos into Node Red to make this map. Colos is what is known in TTN terms as an integration. The process begins by applying for membership at Colos at this address. This is a single application with the next step described in the resulting email and a login here. Head for Products and Semtech LoRaWAN Localization and click on Subscribe. The profile and subscription page appears with primary and secondary keys that can be copied and pasted. Return to the TTN site application. Click on Integrations and add a further integration. Enter any process ID. Then enter one of the 3 access keys. The key selected will determine whether the location calculation is made from signal level, time of arrival, or time of arrival enhanced by Wi-Fi data. Enter the subscription key and this completes the phase. Save the details. The final step is configuring Node Red. Drag out the TTN node and complete the field. The function node contains the message formatting details. And finally, configure the world map to suit your local requirements as before. Press Deploy to complete and start the flow. Holding down the Ctrl and Shift key and tapping M is the shortcut for opening the map page. There will be a short delay, but if all is well, the position button should soon appear. The path in Node Red is therefore the connection to TTN with the details of the application and device, the formatting of all of the gateway details ready for transmission to Colos for their processing before the conversion of the string for onward transmission to the world map that's configured with your local parameters. One final enhancement will be to display all of these results on the web for public view, but do take care with setting up Node Red before making this move. So this completes this video. As usual, it's covered quite a lot of ground, and I hope that it's made some sense. If you have been, thanks for watching.